Hello guys, and welcome to the DSA full course playlist, where in the last two videos we discussed about the sortings. We started with bubble sort, and then we also discussed about selection sort, how bubble sort and selection sort are different from each other, and we discussed about their time complexities and all. Alright, so we'll be moving on with the third one. The third one we are going to discuss today is insertion sort. Insertion sort. All right. So we'll see what insertion sort is, how and why can we use it, how it's different from the other two, the first two, and the logic and application behind the insertion sort. All right. So let's take an example. Um, we'll take the same approach. We will be sorting it in ascending order. All right. So let's take a few elements, 15 and 20 and 6. All right. So we are given an array, and we want to sort it in insertion sort using insertion sort. Now if you remember, if in the first two sorting methods, in bubble sort and selection sort, we would whenever we applied the loop, the outer loop and the inner loop, it would sort the elements from the end position, meaning the biggest element would be sorted first in every iteration, and then so on so on. It would go from right to left. um, Same goes for selection sort. So in there, the 20 would be placed over here in the correct position after each iteration, then 15, then all the bigger elements would be sorted first. So that would be, we can say that it's a right to left approach, but insertion sort is exact opposite. We can say it's from left to right. Left to right, meaning if we want to sort the array in ascending order, then it will be sorted in ascending order from left to right. All the smallest elements, all the smaller elements will be sorted in order. So let's the end result would be something like 1, 3, 7, and so on, right? And the last element would be 20 in this array. So when we say left to right, again, the time complexity of insertion sort is same as selection and bubble sort, which is big O of n square, meaning we will be taking two loops. The outer loop runs from 0 to I, n, which is 7 in this case. 0 to n minus 1 basically means 7 iterations, and the inner loop, that's where we will be applying the logic of insertion sort. So what does insertion sort basically mean, and what does it apply, and how does it apply over here? So we'll be saying that the basic logic, and in the most simplistic way I can explain, that insertion sort takes place in chunks. Now what do we understand when we are talking about chunks? So it will sort the array in chunks. In the very first round, it has 0 chunks, meaning there are no chunks over here. It will take the account of 10. It will take in account the 10. So again, like I said, it will be taking the outer loop and the inner loop. So let's see how that goes. The outer loop runs from 0 to n minus 1. So in the 0th round, we'll be taking the n, 0 and the first element, those two. So two pieces inside the chunk, right? So when we say we are taking two pieces inside the chunk, the second one will be the after the ith. So 10 and 7 will be compared. Now the inner loop, here's where the comparison happens, that 7 will be compared with its predecessor. If it's smaller, means if 7 is smaller than its predecessor, mean the element behind it, then it will be swapped with its place, right? So 7 will come in 10. Now since we are taking the very first round, it will only compare the first two elements. So the array would something, after swapping 10 and 7, the array would look something like this. I'll write over here So the main array also looks in the main array can also be seen in the screen. Alright, so 7, 10, uh, 10, 3, 1, 15, 20 and 6. I put a bracket inside the main array for 7 and 10, and that's the main reason that now we are taking consideration of this. The chunk is created after the first iteration. This is after first iteration. Alright, so a chunk is created. Now when we talk about the second iteration, meaning when 3 is considered inside the main outer loop, inside the inner loop, when 3 is considered, it will be considered to sort, to be placed in its correct position within this chunk. Let me change the color so it becomes a bit more clearer. So it will be considered to be placed and sorted in this chunk inside 7 and 10. So where does 3 apply over here? We know that 3 is smaller than both 7 and 10. So when 3 will be compared with its previous element, we know that it's going to be less than it. So we will be swapping it. So it would look something like 10, 7, and 7, 3 and 10. Now the loop is not over yet. We are again going to compare it with its previous element. You see the inner loop will keep on running till all the elements are reached. Like all the elements that are smaller, that are greater than the previous, than the one we are comparing, all those elements will be compared. Let's say we have also got something like 0 over here. So 3 will be compared till 3 is greater than the element that is before it. That's the main logic. So yeah, in this case 3 is greater than 7, so it will be swapped with it. So it would look something like 3, 7, 10, and then the remaining part of array will be considered 1, 15, 20 and 6. Now this is our main new chunk. We added 3 into this chunk, right? So this is our new chunk. Now again in the next round 1 will be considered to be sorted and compared with all the elements where 1 is greater, till 1 is greater than the element before it. So yeah, it will be compared with 1 with 10. Yeah, that's the true case where 1 needs to be swapped. Then it will be compared with 7. Yeah, 1 is also less than it, so it has to be swapped. Then it will again be compared with 3. As long as 1 is greater, as long as 1 is smaller than the element before it, it will keep on be getting swapped with that element till it reaches the correct position. So in the end it would look something like 1, 3, 7, 10. That's our new chunk. Then 15, 20 and 6. That's correct. That's how all the elements takes place. Now let's talk about the next iteration, because this one's good. We'll be considering 15 this time in this round. 15 will be considered to be placed and sorted in this chunk. Yeah, so we know that 15, from the common sense we can say that 15 is going to be bigger than all the elements inside the chunk. All the elements are less than the chunk. Now like I said, the element which we are going to take into consideration, it will be compared with all the elements till it has found something that is smaller than it. Like over here 1 is going to be compared till 1 is greater than the previous element, but in this case 1 is less than all the elements, 10, 7 and 3, so it got compared with all the elements. But in case of 10, yeah, all the elements, right? So 15 in this case is exact opposite, where it is greater than the previous most element, which is 10. We are comparing from the last. So does it also mean that if 15 is going to be greater than the previous most element, which is 10, and 10 we know that it is bigger than all the elements behind it, then why do we need to compare with all the remaining elements before 10? We are comparing 15 with 10, right? And we know that 15 is greater than them. Then first of all, we don't even need to swap it. But we also don't need to even consider all the previous elements behind it because we are not swapping it, right? Our main condition is that jth element needs to be smaller than j minus 1 element. This is j element, this is j minus 1 element. We know that j element, which is 15, is not smaller than 10 over here. So we don't swap it. Don't swap. Don't need to unnecessarily swap it, right? Because that will break the loop, that will break all the conditions. Alright. So 15 stays as it is, and it will be considered in the new chunk 3, 7, 10, 1, 3, 7, 10, 15. That's our new chunk. Then we got 20 and 6. Alright. Again, same case goes with 20. It will be compared with this one, which is 15. Sorry. So if 15 is less than 20, so if jth element is greater than j minus 1, then don't swap. Don't swap. That's the main logic. We don't need to swap it. We will only swap till it's not greater. Means the previous element is going to be bigger, then only then we will swap it. 15 is not greater than 20, so we don't need to swap it. If 15 was greater than the element after it, then we need to swap it, and it keeps on happening till the element which we are comparing finds its correct position in the chunk. So 20 will be considered in the loop. So 1, 3 in the new chunk. My bad. 1, 3, 7, 10, 15 and 20. And the last element is 6. So 6 is the new element, that the last element that needs to be placed inside the chunk, sorted in a sorted order. Alright, so 6 will be compared with 20. Yeah, that's correct, the swap needs to happen. So 6 will be placed over here. Now 6 will be compared with 15, and yeah, that's also correct, the swap needs to happen over here as well. So 6 will be placed over here, then 6 needs to be compared with its next previous element, which is 10 in this case, and yeah, 6 is smaller, so it needs to be swapped over here. So 6 will take place of 10, then again it will be compared with the previous element here. If 6 is greater than the previous element, then no, we will swap. We won't swap. It found its correct position, but no, since that is not the case, we need to swap it. So 6 will come over here and 7 will come over here. Then 6 will be compared with its previous element, which is 3 in this case. Now here we know that 6 is not great. 6 is greater than the previous element, so we don't need to swap it. So it found its correct position. So after finding its correct position, all the swappings took place. 1, 3, 6, 7, 10, 15 and 20. So the correct array is sorted. Now, like I said, let's talk about time complexity. Since we are not taking any extra space, so the space is going to be constant. And time complexity, like I said, we are taking the outer loop, which will run from 0 to n minus 1. So n, and then each time we are taking the iteration into consideration, the element, the inner loop will run from its second from the iteration plus 1. So if you are taking from I times 0 to I times I n times n minus 1, the I runs from n minus 1 till n minus 1. Then the j will run from I plus 1. So j is equals to I plus 1 within the ith. So it will run big O of n square times. So basically we are running the 0 to n minus 1, and within that I loop we are running the j loop, which will run I plus 1 times. Every time it will start from I plus 1 till n. So no, basically not till n, it's running in the backwards condition. Sorry, my bad. Let's write the code, pseudocode, so it gets more clearer. Alright, so we are taking for I is equals to 0, I less than n, where n is a dot length minus 1 and I plus plus. for, now we are taking j. Since we saw that j will be starting from I plus 1, j will be getting compared with all its previous elements. So j needs to go on, in the worst case scenario, j will go on till it reaches the very first index, which is greater than 0, and j minus minus. Alright, now this is very basic. We are simply checking that if array of j means the one that we are taking into consideration is smaller than array of means the element previous it before it. Alright, so if that is the case, we swap it. Here we swap it, right? Alright, so this is the if block, and here we also, alright, so how do we optimize this big O of n square, right? We saw that here, let's talk about 6. Yeah, we found that 6 is getting compared with 20, 15, 10 and 7, right? Since 6 got compared with 3, we saw that 6 is greater than 3, so it found its correct position, which is after 3. But we also concluded that it doesn't need to be compared with 1. But according to this logic, yet we are comparing it, we are going to compare it with every element. We are not saying it will be getting swapped, we are saying it will run this one, means it will be compared at least. But why do we even need to compare it, right? Means if this condition is false, means if it's already in the correct position after a few swaps, or maybe in the very first time only, then we don't need to even go behind and compare every element. So we can simply say we can break, because that part is already sorted and it's placed in the chunk correctly. Alright, so the main outer loop completes, and we can simply return the array. Yep, so basically we can say that this is the main block of code, and we can simply take the array only as as part of the argument. Yep, so like I said, the complexity is big O of n square, and we simply need to apply a break over here, to not take the other unnecessary elements into consideration. So it's kind of optimized, but when we talk about best and worst cases, it's obviously big O of n square. So let's talk about those cases again. So again, like I said, I'll be repeating that part again, that in the best case, it's already sorted, right, the way we want it. If we are asked to sort it in ascending order and the array is given in ascending, then it's sorted in the best case. Same goes for descending order. In the worst case, like I said, is sorted in opposite way, as in if we are going to be sorting it in ascending order, then we are given the array in descending. That way the worst case scenario means big O of n square will be taking place, all the elements needs to be reversed in its correct place. And similarly, if we are given the array in descending order, and if we are asked to sort it in ascending order, then again it's the worst case for that array. So yeah, and one more thing to point out, that amongst all three sortings that we discussed as of yet, the bubble, the selection and the insertion, the bubble sort takes place from sorts all the elements from right to left. Same goes for selection, it will also sort the rightmost element first and keeps on going backwards. And for insertion sort, it will be sorting the leftmost element first, right? That's the case. Alright, so we saw three types of sortings. Basically all of these have the big O of n square as of time complexity, and the space complexity is constant. No, it's constant, we are not taking any extra space. This is basically when we talk, by the way, it's a simple concept to understand that when we talk about the constant space, meaning we are not taking any extra input of array, or we are not declaring any array or anything. So when that is the case, we can say that we are changing the array in place. This is the in place sorting in a short form, meaning see here we are returning the array. Why are we returning the array? Because we took the array as a part of argument over here. Like I said, we are not creating any extra element for here that we are going to return it, or maybe we are storing something, or no, that is not the case. We are actually taking the array as part of the argument. uh, like over here, uh, array is equals to 1 3 10 15, and we are going to pass this same array as the part of our argument. So this is called in place. This is called in place, and it's a very good practice that we don't use extra space. But there will be future videos and future classes where we will be talking about extra space, because if we don't use extra space, then the time complexity will go out of hands. Maybe there could be some complexities where n square is looking much better case, but there could be some cases where it's inverted, means 2 raised to n, which is usually the case in recursion. We'll be talking about recursion in future cases. We'll be getting there. Like I said, the further 2 or 3 more sorting videos will be taking place after we complete recursion, because we can't understand the logic and application of merge sort or quick sort. You know, we can't understand that without understanding the application of recursion, the recursive tree and all, right? So that's all for today's video. In the next few videos we'll be covering, I think one more sort is remaining, maybe cyclic sort, and then we'll be taking a video about all the questions. All right, thank you.